is a schematic diagram of the standard penetration test. So you see the hammer, the anvil, and you see the splits, the sampler, that's the split spoon sampler. So after the first increment of 150 mm, that is the sitting drive, which is usually not taken into consideration. Then the next increment, that's the second increment, is another 150 mm increment. Then the third one, another 150 millimeter increment. So making a total of 450 millimeter per increment. That's the total of 450 millimeter to consider the number of blows. Okay, moving on. So I will show you a short video of the SPT. So this is a short video. So you can see the hammer. This is an automatic SPT machine. So the number of blows is what determines the end value. That is the end value. Okay. Now let's check out. This is a manual. This is a manual SPT. So you see this. You can see the blows are taken manually. Okay, let's move on. So there are various factors that can influence the end values gotten from the SPT. Like when you have inadequate cleaning of the hole, that can cause an increase in the end value. When you do not maintain an adequate water level in the borehole, that is, the bottom of the borehole may become quick and loose, so which can reduce the end value. Also using an inaccurate hammer weight, because a weight of, like we saw in the previous slide, that a weight of 64 hammer, that the hammer weight should be 64 kilogram, or using a height, taking the blows at a reduced height of, say, less than 760 millimeter height, can also alter the end values you get from the site. Okay, so let us move on. So when you take careless blow counts, or you use a non-standard sampler, this can also affect the end values you get on site. And when the sampler hits a coarse gravel or a cobble in the soil, this can cause an increase in the end value, because when you keep hitting, the end value tends to increase. Or when you have a bent drill rod, this can increase the end value, and it will not really show the present situation of the soil, this current condition of the soil. Okay, moving on. So there are some limitations of the SPT. There are some of the limitations, like the SPT gives erroneously high and unconservative values in soil containing coarse gravel or boulders, like we said earlier, because the sampler would be obstructed. You know, when you're taking the blows, the sampler will be obstructed because of those coarse or gravel. And in soft or sensitive clay, the SPT gives inconsistent results compared to the actual in situ condition. And if the water head in the hole is not maintained, like we said before, or if it's not maintained above or at the ground level, piping can occur. We can make the soil quick and loose, and this can reduce the end value. Okay. Okay, let us go back. So because of all these variations in site conditions, this brought about the SPT correction. That's why we have the N60 and the N160. So I'm going to be explaining the N60 and the N160 correction. So the N60 is the SPT end value corrected for field procedures, while the N160 is the end value corrected for, the SPT N60 is corrected for field procedure, while the N160 is corrected for both field procedure and overburden pressure in sand. So the N160 correction is basically for corrections in sands or in correctionless soils. So there are several types of hammer that are used for the SPT, like we saw in the two videos. So we have several hammers, and these hammers have different efficiencies. They have their own efficiencies for energy dissipation on the sampler and the surrounding soil. So in order to reduce the significant variation of the SPT values due to the difference in the energy delivered by different armors, it has been recommended that the end value should be standardized to 60% energy. That is what brought about the N60. That's what brought about the N60 correction factors. So according to Skempton 1986, it developed an equation for the N60, factoring in the armor efficiency, the borehole diameter, the sampler, the rod length corrections. So that is what constitutes the N60 values. And okay, in this slide we see various corrections for the SPT N60 value. We see the different types of armor. We see the different type of armor and their efficiencies. We see the corrections for the borehole diameter, that is CB. So for different diameters of borehole, we have correction for that. The variation in the sampler, we have correction factors for that, and also the rod length, we have corrections for that also. Okay, moving on. So there are some from several investigations, it has been proven that the end value, that's the penetration resistance, is dependent on overburden pressure. That's in cohesionless soil. So if there are two granular soils with the same relative density, the end value will be higher as the depth of the soil increases, because the soil increase in the confining pressure. That as you go down for the same soil with the same relative density at different depths, like at a shallow depth, you tend to have lower N value compared to that of at a higher depth due to confining pressure or overburning pressure. The N value of a soil at a shallow foundation, like I said, will be lower than the N value of the same soil at a greater depth. This brought about the N160 correction. So Lyle and Whitman gave this relationship. Kempton also gave this relationship relating overburden pressure with the correction factor. So we also have Seed 1975 relationship and Peck's relationship. Okay, so moving on. So Jeffries and Davis 1993, it suggested that the best way to get the SPT end value was to get it from the CPT. That's to convert the QT, that's the cone resistance, from the CPT to an equivalent SPT end value. That's SPT end value at 60% energy dissipation using the soil behavior side, that's the IC value. And this equation was modified by Robertson and Wright 1998. He gave this relationship that's relating IC with the cone resistance from the CPT, and the relationship for IC is gotten from this relationship here. All right, so moving on. So the Clayton 1993 gave these soil classifications based on the corrected N60 and N160 value. You can see for sand, he correlated the N160 value for sand with for its classification, sorry. And for clay soil, it correlated with N60. So for N160 values of 0 to 3, it's very loose. From the N values from the N160 value from 3 to 8 is loose, and so on and so forth. And also there are correlations, different researches and investigations have shown that there are correlations with friction angle. That's the SPT corrected and SPT N values have been correlated with friction angles. Atanacha and Uchida 1996 gave this relationship. So when you have your N160 value, you can get the peak friction angle. Also, Peck 1974 gave this relationship relating N160 with friction angle. Wolf 1989 proposed correlating the N60, correlated N60 value with friction angle. Schematman rather 1975, he correlated the N60 value along with the overburden pressure to determine the friction angle. And in the INSITU GEO software, the INSITU GEO software gives you from your raw end value gotten from the gotten from the site. It gives you the N60 and N160 value. Also the N70, that's correction at 70% energy dissipation. And also it gives you geotechnical correlations, as we'll see shortly. It gives you estimated unit weight, estimated relative density, friction angle, on-drain shear strength, and so many other parameters. It also gives you graphical representations. It designs the shallow foundations and also the deep foundations. There's a research paper that will soon be out. A research paper will soon be out that models Tezagi's bearing capacity equations together with the corrected N values. Okay, and the good thing about the software is that you get all the equations used in the software and the software manual. So you get all those in the software manual. You get the references from the software manual. So all the equations used in the INSITU GEO software has references. Okay, so that will be all for the presentation. Now we move to the INSITU GEO software, how to use the software to analyze this data. So I'll be sharing my screen. I'll be sharing my screen of the INSITU GEO software so you see how this works. So because of time, we have already input some demo data. So here in your input general, you input the project name, the test location, the type of method or the standard you used in carrying out the test, the borehole test number, the reference, the job reference, the weather condition while carrying out the test, the dates, the groundwater level depth. So, you know, these are important parameters that must be inputted for you to get correlations. So you input the groundwater level depth and also the water or mud level in the borehole, that's at the start of the test. And also you have to input the maximum test depth. That's the maximum depth at which you carried out the SPT. Okay, those are the important parameters you must input for you to get correlations. So, okay, ground level, that's the ordnance datum you input if available. Then the name of organization which carried out the test, the details of the organization, the test operator was checked by or approved by. So you select all this, okay. And for the type of armor, you know, different, like we said earlier, different armors for the SPT has different efficiencies. So you select any armor from the drop down. Then if you select it, the software automatically detects the armor efficiency. So if the armor you use is not here, so you just click others, and you know, then the armor efficiency of 0.6 will appear. So the efficiency of 0.6, you know, from this note it says if the value is in percentage, please divide by 1000. Say if you are not sure of this, input a value of 0.6. A value of 0.6 efficiency is advised. So you input the borehole diameter in millimeters, then the type of sampler, if it's without liner or with liner, and also the SPT correction used. Like from the slide I shared with the previously, that's from our slides, we saw different researchers and their correlations with the SPT, that's the SPT corrections. So I select Robertson and Wright, which is the latest research. Okay, then the drill rod size length you used during the test, and if a casing was used, yes, then you can select the soil classification. Some engineers still use Tezagi and Peck, but Clayton 1993 is recommended because it's the latest research. So I click Clayton 1993. So if there are any observed events during carrying out the tests, you input here. So now this is the input table. This is where we input our INSITU data. So at a depth of 0.75, so that's 0.1. At 0.1, I type in 0.1. Then here I click test sample. Then I select the type of soil at that depth. If it is clay, so I select clay. If it's silty sand, I select silty sand. Then for the sitting drive, like I said, the first 150 mm penetration is not recorded. That is for to avoid sitting drive error. So you input these values. These values are not used for, are not part of the SPT-N values used for correlations and calculations. But the values, the N values from the test drive, you input it here. That's the number of blows at 300 mm penetration. That's after the second and third increments. Then you input the soil color, and if there are other remarks on the soil, you input it there. So at 0.75, then I input at the next point, 2.25, that's 0.2, test sample. Then I select the same way I did for this, I do for here too, at this depth. So I select the type of soil at that depth, then the N value, that's for the test drive, and at what depth, then the color. So I repeated this process till the maximum test depth. My maximum test depth for this demo data was 20.25, yes. So at 20.25, I have test sample, the soil type was fine or silty sand. Then this is the the sitting drive at 150 penetration, and the test drive at 300 mm penetration. So say I have the next point, say at say, let me just do input a value at one point, say at 0.15, then I have a test sample, select test sample, then I select the type of soil, say it's well-graded sand, then say I have N value of 4 for the sitting drive at 150 mm penetration. Then the test drive, say I have 28 at 300 mm penetration. Then the soil color, I type it there. So that is how to input data in the software. That is for the SPT. Okay, so now let us check out our correlations after we input these data. So, okay, let us click to move to output table. Yeah, so we see the soil description based on the soil classification system we chose from our input general. So we chose Clayton. So it gives us, based on the corrected N values, it gives us the soil description. Like this is medium, grave, fine or silty sand, like that. So it gives the soil description to the maximum test depth. So you get your N60 correction, that's correction for field procedure. You get your N160 correction, that's for cohesive soil, that's correction for overburden pressure and field procedure. You get your N70 correction, and also you get the estimated unit weight at each depth based on research and correlation. Like I pulled up from the other slide, we saw that there are correlations with the corrected N values and some of all these shear strength parameters and some of all the soil properties. So we have the estimated unit weight at various depths in kilonewton per meter cube. We get the estimated QC, that's the estimated cone resistance from the N value, just like we have estimating N values from the cone resistance. We also have estimating cone resistance from the N values. Okay, so we have the relative density for cohesionless soils. We don't have a value here because the soil at this depth was a cohesive soil. It's silty clay, so you don't have a value for the relative density. So the software gives values for relative density for cohesionless soils. So we have those values, and also you have the estimated friction angles for cohesionless soils. We don't have here because it's a cohesive soil. Okay, we get the friction angle at those depths. So, but for the cohesive soil, we get the estimated undrained shear strength. So if we add cohesive soil all through, so we are going to have undrained shear strength values at those points. Also, we get the estimated over consolidation ratio value, and we get the estimated unconfined compressive strength. It is noteworthy to it is worthy to note that the SPT is actually good for cohesionless soil. That's for sand materials. They give reasonable values. They give reasonable correlation for cohesionless soil. Okay, and we also get the estimated shear wave velocity in meter per second at each depth, at each N values. And if we input any other remarks, we get it here. Okay, so moving on from the outputs, these are the output, these are the correlations the software gives. So let us check out, okay, before we move to the foundation, let us check out the graphical representations. So the software gives graphical representations. We get the penetration resistance versus the depth, the N60 versus the depth, the N160 versus depth, the N70 versus depth. We get the estimated unit weight versus the depth, the estimated cone penetration resistance versus depth, estimated relative density versus depth. We have the estimated friction angles versus the depth. We have the estimated shear wave velocity versus depth, the estimated unconfined compressive strength versus the depth. That's for cohesive materials. Same thing for OCR versus depth and undrained shear strength versus the depth. So these are the graphical correlations or graphical representations you get from using the software. So let us check out foundation designs. So for foundation design, this session is for shallow foundations, and this session here is for deep foundations. So we input the footing depth, at what depth we are on the footing, then input the tolerable settlement. However, 25 mm or less is recommended rather when using the SPT. That's for the tolerable settlement. And here you can select the footing section type. This is square, rectangular, circular, or strip footing. Say rectangular, you have to input the footing length. But for this, let us work with the square. Okay, then load on footing. If you have a load on footing, you can input it. You see, the software even says is that the parameter does not directly affect the bearing capacity. If you, from your structural analysis, if you know the load coming on the footing, you can input it there. Then the factor of safety of 3 is recommended when using this test. Okay, so let's check out the results, the bearing capacity result, before we move to the deep foundation. So output foundation. Okay, for a footing depth of 1 meter, we have the net allowable bearing capacity of 145 kilonewton per meter square, and we get an elastic settlement of 20.72, which is still within the tolerable settlement we input in our input foundation section rather. So you get the net allowable bearing capacity. So that is for the shallow foundation. So let us go back to the input foundation for let us design a pile foundation, a deep foundation. So we select the pile section type, be it a square pile or a circular pile. Then we select if it's a bored or driven pile. The bored pile calculation is based on Descartes 1995, and that of driven pile is by Mayer of 1956, because we found out that the pile capacity for these researchers gave were very conservative and meaningful. So at a pile depth of 15 meters, our test depth was up to 20.25 meters. So let us install our pile at 15 meters depth, then a pile diameter of 450 or whatever pile diameter you want to input, and also the pile group section length, width. That is if you have these values does not affect the pile capacity. They are just used for elastic settlement calculations. Okay, so you input the pile group section width, pile group section length, and if you have the load coming on the pile group from structural analysis, you can input it here. And a factor of safety must be inputted. As a factor of safety of 4 is recommended when using the software. That's for the pile foundation. You can as well use your engineering discretion to input the factor of safety you want. Some engineers use 3, but a minimum factor of safety of 4 is recommended from researches and papers. Okay, so let's check out the output. So at 15 meter pile depth, we have an ultimate load of this. Then the allowable load for a single pile is this after dividing by a factor of safety we input. So we have the safe load or allowable load for a single pile as this in kilonewton, and also we get the elastic settlement of group piles. Get the elastic settlement of group piles. Okay, that is the output foundations. And also the SPT in the INSITU GEO software comes with an assisted mode. So let me click. So from the input general, you can see click to move to assisted mode. This assisted mode helps it just helps you in foundation designs. So anything you input in this primary SPT automatically reflect. That's all your inputs from the site that you put in this primary SPT. When you come to the assisted mode, it brings it automatically. So you don't need to input that again. So these values are already there automatically. So you just need this assisted mode is for foundation designs. This one assists you. It assists you to probably estimate the load coming on the footing. Okay, so for the input foundation, let's say for a footing depth of 1 meter and 25 mm tolerable settlement for a square footing, and a footing width of say 1 meter. So automatically it assumes the load. You see, okay, let me remove this value. So say for a footing depth of 1 meter, a tolerable settlement of say 25 mm, then a footing section type of, let me select a square footing and a width of 1 meter. So automatically it assumes this load on footing from the bearing capacity. So this assumed load is gotten from, the bearing capacity is in kilonewton per meter squared. So the assumed load is derived by using the multiplying the value for the bearing capacity by the area of the footing. So let's check out the output foundation. So we have the bearing capacity of this and the elastic settlement of this. This is the same value we add from the primary SPT. You can see we have the same values. So this assisted mode is just to help you estimate the load coming on the footing. That's if you don't know the load from structural analysis, it just assists you. So you can use whichever one, either the assisted mode or the primary version. You can use it. It still gives you the same value. Okay. So for the assisted mode, for the power foundation section, so we select the power section type, and if it's a driven or a board power, then we input the power depth, the depth at which we want the power to terminate. Okay, let me say I want this to terminate at a 14 meter depth. Then I input the power diameter. Then I select the power spacing, either 2 times power diameter or 3. 3D is mostly used. Okay, and the number of floors from superstructure. This one helps you estimate the load on footing. So a column load of 500 kilonewtons is assumed per floor. So if I have one floor, I have a load of 500 kilonewton. If I have 2 floors, that's 1,000 kilonewton. You just estimate the load. So let's say for 4 floors, I have a load of 2,000 kilonewton. Then automatically it calculates the power group section width and length for me. Then it also calculates the number of piles. The number of piles I need. And also I have to input the factor of safety. The factor of safety of 4 is recommended. So I can click to output foundation. Then I also get the value, the safe load for a driven pile. Note that I selected a driven pile in the input foundation section. So this is the allowable load for a single pile. And also I get the elastic settlement. I get the elastic settlement of pile group as 30.78 millimeters. So I can decide to change, the pile installation type, or say the diameter of the pile. I can decide to change it. See, automatically it calculates the number of piles I need for a board pile at this pile diameter. That is the usefulness, or that is what makes the assisted mode different from the primary version. So output foundation, I also get, I have allowable load, that's a safe load for a single pile as this value, and also I get the elastic settlement for this pile diameter. So I can decide to change the pile configuration, size. I can change the size, and I can play with the values and get the load I need. So that is one important thing the assisted mode does. Okay, so this is the primary version. So you can decide to print your work. Okay, we have a result sheet. Let me move back to the from the input table. So click to move to output foundation. This is the output from the foundation. So I have a result sheet. The INSITU GEO Software has a result sheet that has all your, all your graphical representations, your inputs. So this is a presentable result sheet. So I have all the inputs. I selected the correction, referencing and write, the ball diameter. So all my general details are here. The bearing capacity values, the settlement values are there. The power foundation designs too are there. I also have all the graphical representations. I have all my graphs, all the graphs based on the input. Also for the assisted mode, you have this also. And I can get all my correlations at the various depths. So you see at various depths, I have the result sheet that shows the soil description and all the outputs I get from the software. And this result sheet can be printed either for the primary version or from the assisted mode, whichever one you choose to use. You can just press Ctrl P on your system or file and come to file and click on print. So you can print the number of pages you want. This is page 2, page 3, page 4. So you can decide to print the pages you want. Say I want to print from page 1 to page 5. So I just click print, then it prints out the result sheet in a presentable form. And I can also attach this results sheet to my soil report. You can attach it to your soil report. And also you can save your work as a PDF. You can save the result sheet as a PDF. So just click on Microsoft Print to PDF from this portion. So it automatically converts your result sheet to a PDF format. And also you can save your work. If you want to save your work in a .coms format, just file, then save. So you can save your work just the normal way you save. You can save your work. Yeah. Okay. So that is it for the analysis with the INSITU GEO software. So you see, with the INSITU GEO software, you get correlations just from your end values. That's just from the end values you get from the site, and it gives you correlations of the N60, N160, and these correlations are precise enough. They are correct. Even they can be compared to what you get from laboratory analysis. The values are very close when you conduct laboratory analysis using the same N values. That's the same value. So that brings us to the end of this webinar. So I'll be entertaining questions. If you have questions, whatsoever on the software, be it on the slide or whatsoever, so you can use the raise hand sign so I can answer your question if there is any question at all.
Thank you for the session. We really appreciate your effort.
Yeah, thank you, sir.
Yeah, please. You said these n values. I want you to elaborate. How are they gotten? Is it from experimental stuff on the site, or they are assumed values?
Okay, thank you very much, sir. So initially, I put up a slide explaining some of how these correlations were determined. Okay, for the N60 value, for the N60, Skempton 1986 gave these correlations. That's it, to get the correction for field procedure. So this is the equation used in determining the N60 value. That is this. That is the efficiency of the armor multiplied by the correction for the borehole diameter sampler correction, the rod length correction multiplied by the N value. That's the N value you get from the site, all divided by the by 0.6. This equation was given by Skempton 1986. So these are some of the armors and their efficiencies and the correction factors. Like for the borehole diameter correction, that's the CB, the sampler corrections, you have these values, and the rod lengths based on what you used on site. So these are the correction factors. And for the overburden pressure, the N160, that's the overburden pressure correction. These are some of the relationships used. But for the INSITU GEO software, the references for all the calculations are present in the manual rather. So the INSITU GEO software for the N160 value, uses, for the N160 value, it uses research from, okay, from, sorry, yes. So it uses this relationship. It relates the N60 value with the N160 value. That is what the INSITU GEO software uses. So this is how we get the correction for the N values now.
Okay.
Yeah.
Thank
Is
you.
there
Thank you, sir.
is there any other question, or is there any way you're not clear with, sir?
Please, we need the email.
You can send us an email. Then we have a one-on-one meeting. If you have questions or anything regarding the software, or things you're not clear about, you can just send us an email and schedule a Zoom meeting with us. So we are ready to assist you. We are ready to help you. And I hope this webinar has been an interesting one, and I hope you've been able to gain from it. And we at Com Software really appreciate your presence. We really appreciate you for taking out time to join us in this webinar.